Welcome to Talkcast, and it's episode 119, and the 8th, I believe, in my series on the science of can and can't, the book by Chiara Marletto, all about constructor theory. And today it's a video because there's going to be diagrams, movies, and even real-life experiments, such as are going on in the background, which you may hear a little bit of a ticking. The motion of a motor, an engine, a heat engine, specifically something called a Stirling engine. These things, these objects, these devices, pieces of technology, have helped build the advanced society around us. Well, the explanation for their operation comes down to the field of physics called thermodynamics. And that's what this chapter of Chiara Marletto's book is all about. Now let me grab a hold of this really interesting, but simple yet subtle piece of technology. So here it is, still moving actually. What it has are two surfaces, one at the bottom, one at the top. The one at the bottom can be placed in contact with a heat source. And over there, that's nothing but a hot cup of water. And at the top, it's cooler. Hot down here, cold up here. And in between is a diaphragm. And the diaphragm is moved by gas beneath expanding. Because it's heated gas expands, increasing in volume, pushing the diaphragm up and doing work, as we call it. So heat is able to be converted into work. And this basic principle is the principle of all such heat engines, a foundational part of not only technology, physics itself, and why Chiara has devoted an entire chapter of her book, in part, to this phenomenon. But there's more. There's an even deeper reason why anyone would be interested in such a thing. Put it back over there and you can see that although it's stopped now because there's no energy being supplied, we can put it back onto the hot water. Nothing happens. We need to give it a little push to get it started. And there we go, we're off again. So what's happening is we have high energy of a type that we'll talk about throughout the course of this episode in the water, which is in the cup there. That heats the gas that's in the cylinder here. The gas, when heated, expands, pushing the diaphragm up. It's connected to a piston. The piston drives the spin wheel. And that, in theory, could be used to do work of some kind. And that is what work is, force over some distance. And in theory, you could hook that thing up to a generator. A generator, a series of wires moving in a magnetic field, which would generate electricity. Again, one of the fundamental features of our modern civilization. All down to simple devices like this. But as we'll see, although simple, there's a whole bunch of really interesting subtleties that we're going to get to today. So what a really curious thing this is. Let me grab a hold of it again, being very careful because it's actually filled with near boiling water to get the thing to work. And essentially we will come to three important parts of this in order to turn the energy that's in the cup into the energy of work, the capacity to move stuff around. What that is somewhere that's hot as well as somewhere that's cold. There needs to be a temperature differential in order for there to be a transfer of energy by heat from the hot place to the cold place. And by virtue of that temperature difference, we do get this movement of heat. And the movement of heat, that's the thing that's able to do the work. But why should it happen at all? What's really going on in terms of the physics here? Well, that's what we're going to talk about in part today. I might remove the motor for the rest of the episode. Otherwise, I think it's making noise in the background. Okay, there we go. Now today there won't be many, if any, readings from the book itself. This is more like a prelude, and I've done this a few times. I think that the topics are so interesting that are in the science of can and can't. The topics are so interesting in and of themselves that sometimes I like to step outside of the book for a moment just to discuss some of the physics absent the book. Now the reason for this is because constructor theory, remember, is a new mode of explanation, of those concepts, of those things, such as we're going to be talking about today, thermodynamics, and as we've previously talked about, knowledge and information, among other things. So this Constructor Theoretic mode of explanation is a new way of looking at things that we already know about, to try to come to a deeper understanding of things, to try and answer some of the unanswered questions. And therefore, constructor theory is touching on topics that have a history in science. And today is a prime example of that. The very title of the chapter, Work and Heat, will scream out to anyone who's done physics or chemistry the topic of thermodynamics. I might move away my little setup here so that I don't spill the water any more than I already have. Thermodynamics is a curious beast. It's one of those subjects at undergraduate level where, unlike quantum theory, where happily early on I was able to sort of uncover for myself, discover by reading some popular science accounts, that the lecturers and tutors weren't giving me the story, because I found the fabric of reality and I encountered David Deutsch through the internet. So happily I understood that my confusion in quantum theory was warranted because I wasn't getting the right stuff in the lectures. I had to go elsewhere in order to find that. But unlike quantum theory, thermodynamics was a field where I got through doing physics, and not until later, when I was actually teaching the subject myself, did I realise that the way I had been taught the subject was itself deeply riddled with misconceptions. I kind of couldn't believe that even after studying physics, I didn't really know what a concept like heat was. I mean, if you'd asked me coming straight out of university, I'm sure I would have had an answer. I would have said something, and I would have been awarded marks on tests, and I would have been able to do calculations of things like specific heat capacity or thermal energy or enthalpy changes and so on. But that's just to say, of course, I was working instrumentally, plugging in numbers into equations that worked to predict the outcome of experiments without ever knowing what was actually, fundamentally, going on. You know, some of these questions are things like, a heater provides heat energy at a rate of 1,000 watts to 1 litre of water. Calculate how long it takes for the water to change its temperature from 20 degrees Celsius to its boiling point at 100. Something like that. But that whole way of asking the question, that whole way of putting the question, is itself entirely misconceived. This idea of heat flowing or some such, or thermal energy moving from one place to another. It took me teaching this stuff, and therefore being challenged myself to really think about this, to really understand what was happening at the level of the particles. What's flowing from one place to another when things are heated? What's going on there? Why are we using this language? Is there some substance coming out of the kettle? And if it's energy, how? What is this energy? It seems like it's almost a spiritual force. This energy flows out of the heating element and into the substance, causing its temperature to rise. How does it work? How does any of this work? I think I can explain it now, but I don't think I could have explained it then. I always heard, for example, that heat flows from a hot body to a cold body, but never in reverse. What the heck is this thing, heat, that's flowing around? Well, the fact is that heat is not a thing. It's not a substance. And the person that taught me that was the great physical chemist, perhaps the most famous living thermodynamicist of all, Peter Atkin. And it took me listening to his lectures, watching him on YouTube, reading his books, especially his textbooks and his popular accounts as well. Let me quote my favourite quote of his on the topic of heat. I mean, there's many, many other concepts in thermodynamics, but heat is possibly the most misunderstood and subtle of all the concepts within thermodynamics. And I find this particular distillation of wisdom on the topic of thermodynamics the most brilliant of all. It's from one of his popular books on thermodynamics that I'll mention again later, but Atkins wrote, quote, "In thermodynamics, heat is not an entity or even a form of energy. Heat is a mode of transfer of energy. It is not a form of energy or a fluid of some kind or anything of any kind. Heat is the transfer of energy by virtue of a temperature difference. Heat is the name of a process, not the name of an entity." So, in grammatical terms, heat is more of a verb than what it is a noun. But of course we have casual English as well. And so sometimes it's almost unavoidable in normal day-to-day conversation in using the word in its less precise meaning, even when you're talking to other physicists and so on, because that's just what we've inherited from the long history of the use of the word and the way in which thermodynamics began and our scientific understanding of this began, of heat being some kind of substance or fluid, even though it's not, because now we understand better. Heat is the movement of energy. But what energy? Well, it's kinetic energy in the main, and that kinetic energy can cause increased kinetic energy of the particles of the cooler body by physical collisions with particles in the hotter body. So conduction of heat in solid metal, for example, happens because not this substance heat is flowing from one place to another. There is no such substance, but rather at the hot end of a piece of metal, the particles there are vibrating really fast and they are physically colliding with their neighbours. And that collision goes all the way along the solid piece of metal until you get this transfer of energy. Kinetic energy, the energy of motion, of vibration of these particles from the hot part to the cold part. That's what heat is fundamentally. Movement at the level of the particles. It's not only that, but as a first approximation, that's a very good way to understand what's going on there. It's not that there is this strange substance flowing from one place to another. Rather, it's just a vibration of particles. And if they're vibrating in one place, they'll be colliding with their neighbours, and their neighbours will collide with their neighbours, and so on. And that's how conduction in, for example, solids like metals happens to work. Now, it's not always that the kinetic energy happens to increase. If you heat something, it can be the case that the temperature will rise, but also, maybe its temperature won't rise. Maybe just its state will change. State changes happen at the one temperature, by the way. So, for example, water, typically at sea level, under the standard conditions and so on, will boil at 100 degrees Celsius. That means that at that temperature, the liquid water is turning into gaseous vapor at 100 degrees Celsius. The liquid water is at 100 degrees Celsius, and the vapor is at 100 degrees Celsius as well. And we're going to get back to exactly what this idea of temperature means as well. That itself is another subtle concept that needs to be made precise by physics. This is what physics tends to do. But people can tend to have this misconception. You put water in a pot on a stove and you boil it. And one of the first misconceptions that people have about that process is that although they understand that the water boils at a particular boiling point at like 100 degrees Celsius, that if you continue to apply the heat, maybe the temperature goes up and up and up. You can ask people this question if they don't remember their high school science, let's say. That's what they tend to predict. After all, you're adding more heat. You're heating the water. You're continuously heating the water. Shouldn't the water continue to get hot? No, it doesn't. It stays at 100 degrees Celsius until it all boils away. When I say 100 degrees Celsius, I mean assuming all the usual conditions. If you lower the air pressure, the temperature at which the water boils happens to be lower as well. But why are there these misconceptions? Well, it's because the teaching of thermodynamics around the world still follows this misconceived pattern. Heat is strongly implied to be a fluid of some kind. Such and such contains more heat than something else. Now, it's fine to say something is hotter than something else, but not to say it contains more heat than something else. And why? Because, again, heat is not a substance. It's not a thing. Kinetic energy is a thing, how fast the particles are moving or vibrating. Potential energy is a thing, how strong the bonds between particles happen to be. But heat is not. Heat is the name of a process, to heat something. And having heated something, the temperature, the kinetic energy or the potential energy stored in the bonds of the particles will have increased. The real goal I'm reaching for in this podcast, and especially the next one, is a more precise statement of something called the second law of thermodynamics in terms of deeper underlying principles or a deeper underlying theory. So here's a bit of pedagogy first, a method of teaching or learning. It's been interesting to me as I've come out of teaching and into doing, well, this kind of thing, among other things, that people will sometimes ask me when I am explaining some aspect of Karl Popper or David Deutsch's work, some deep and subtle part of either philosophy or epistemology or science or physics, they desire, on occasion, a particularly precise definition of certain concepts or terms. I notice David gets this when people ask him questions as well. It's often, if they have the opportunity to interview David or to discuss with him, they will say, well, can you define knowledge for me? Can you define optimism? Can you define this, that, or the other? And David, I think, I can't speak for David, but like me, I guess, following in the tradition of Popper, I think has an automatic kind of aversion to that kind of thing, to trying to define something. Now, I'll speak for myself here. There are a couple of reasons for that. I worry about the term definition and being asked to define things precisely. The first is, well, the idea of having a definition in people's minds, I think, is supposed to capture something of the essence of the thing you are talking about, that you are defining. It's as if you define the term and then you are held to the definition. And people find holes in the definition, but all the while that was never your intention to say everything that could be said about the term. So the problem with definitions, to my mind, is that they have this pretense, in some people's minds anyway, of being final and unalterable. This is the perfect statement of what this term actually means. But of course that's anti-fallibilist and inconsistent with the broader worldview that we can always make progress and learn more. And it's anti-philosophy as well, as we understand the term. Popper even wrote about not wanting to quibble over definitions. He spoke about this and wrote about this in Objective Knowledge. Now, putting all that aside, the other reason to object to providing precise definitions of things is, well, I think people are enacting a kind of meme of a kind when they ask the question, what's your definition of knowledge? What's your definition of energy or liberty? What they want, aside from trapping you in a debate over terms perhaps, which is, again, not real philosophy, is that they might genuinely want to learn, but they want to learn the definition. It's like they're back at school and they want to write their list of words in a glossary, and once they learn them off by heart with their definitions, they can top the test and say they understand all those words and therefore they understand this thing and what they're talking about because they've got the vocabulary and they know what these definitions are. And I think that's just a wrong way of going about understanding reality and understanding philosophy and understanding science as well. But it's the traditional conception that people have about how learning kind of works. I know this is the way I was taught. Here, write a glossary of terms. Here, write these definitions of words. And it's still done today. Teachers love a good glossary at the back of students' workbooks. Now, is this to say definitions are utterly pointless? Well, no, of course not, but you have dictionaries for that kind of thing. The better idea, especially when it comes to subtle and open-ended concepts to some extent, especially in philosophy and science, is to approach the term from various different angles and try to come to a more complete panoramic understanding of the term, realizing the whole time there is no single definition for some of these things, but rather we have an explanation of what this concept is, and we can likely improve it over time as well. So don't learn the definition, just try to understand what this thing is all about. Now, why am I rattling on about that? Why would I be saying that approach to learning is wrong? Well, in this field, in thermodynamics, it's filled with this kind of subtlety and the use of very common words that everyone thinks they know. But in thermodynamics, these words have a certain kind of precision use, one might say, idiosyncratic use. But sometimes that precise and idiosyncratic use can seem to make things more difficult to pass. And so for that reason, I'm going to be doing something else today, in this particularly extended podcast today. Rather than me just telling you, well, here's what energy is, for example, and here's what degraded energy is, here's the first law and here's the second law listing things, here's the definition of, let's say, entropy, which is something we'll get to, and then presuming at the end, once you've understood all those words, you're going to understand thermodynamics. No, we don't want to do that. We're going to talk about the words, talk about some of the definitions, but I want to take a wide variety of approaches to these things from popular science and from the history of science and from mainstream texts as well, and see if and where they converge, and hopefully this will help us create some sort of background knowledge. So then we can understand what Chiara and David are accomplishing with the constructor theoretic view when it comes in particular to the second law, which, as I say, is kind of the goal of the exercise here. I'm going to meander through this territory today to try to come to thermodynamics and the main concepts and the main laws. There are, as usually counted, 4 of those laws, numbered, confusingly, 0, 1, 2, and 3, so that perhaps if you are largely unfamiliar with this stuff, that by the end of this episode, you're in a good position to really get the punchline, so to speak, by the end of next episode. And perhaps if you didn't know much about thermodynamics before, and perhaps you have a casual interest in it, you'll be more scientifically literate in it, let's say, from now on, perhaps. So I'm going to be referring to a few old texts that I'm going to dust off, and my own notes as well from having taught some of this stuff over many years. And I'm going to therefore lean on some of the giants who write in this area of thermodynamics. And first and foremost among them, I've already mentioned the man who's perhaps one of the greatest minds on this topic, Professor Peter Atkin. He wrote some of the seminal and foundational texts on the topic of thermodynamics and physical chemistry, mainly for chemists and physicists and engineers and others who needed some sort of grounding in this stuff. He's the kind of the go-to guy when it comes to thermodynamics. But more than that, he backed up all that heavy technical stuff with some really, really good popular science books explaining the implications of these things, the sort of broader, deeper philosophical implications of some of this stuff. He's got numerous lectures, by the way, online. And again, those online span the highly technical through to the popular and philosophical. So up front, I want to say that today, much of what I am saying comes straight from Atkins, but of course, errors are my own entirely. I just don't want to have to stop all the time and quote him when I'm saying stuff, because many of his words that he's written down will just come flying out of my mouth because I'll be aping what he says when it comes to thermodynamics. Most of my own lessons that I ever delivered on thermodynamics were basically me imitating Peter Atkin as he appeared in print, like that heat quote earlier, which I really love and can almost recite off by heart. It comes flying out of my mouth whenever the topic of heat comes up. And the other guy I'm going to be referring to, and I'm going to read snippets from his work today, is Paul Davies. Paul Davies is, of course, not only an accomplished physicist, but, a polymath of a kind in his own right, and one of the most prolific popular science authors ever. And really, my first introduction to the idea that the second law had anything like deep implications or philosophical implications came from Professor Davies, and in particular, The Mind of God, where I read, well, let me just read that bit for you from The Mind of God to give you a taste of why I was inspired by it, and realize that this thermodynamic stuff is up there alongside quantum theory and general relativity as being the stuff that you want to understand better if you want to understand the deepest theories about the universe. So I've taken The Mind of God here, and I'm reading a little bit of page 46 over to 47. And Paul Davies wrote, quote, "Today we recognise that no star could keep burning forever. It would run out of fuel. This serves to illustrate a very general principle. An eternal universe is incompatible with the continuing existence of irreversible physical processes. If physical systems can undergo irreversible change at a finite rate, then they will have completed those changes an infinite time ago. Consequently, we would not be witnessing such changes, such as the production and emission of starlight, now. In fact, the physical universe abounds with irreversible processes. In some aspects, it is rather like a clock slowly running down. Just as a clock cannot keep running forever, so the universe cannot have been running forever without being rewound. These problems began to force themselves on scientists during the mid-19th century. Until then, physicists had dealt with laws that are symmetric in time, displaying no favoritism between past and future. Then the investigation of thermodynamic processes changed that for good. At the heart of thermodynamics lies the second law, which forbids heat to flow spontaneously from cold to hot bodies, while allowing it to flow from hot to cold. Pausing there, my reflection. Notice here, even with the great Paul Davies, who, much respect, loved dearly as a thinker, he's got the idea of heat flowing there from one place to another. A misconception, I think, not the best use of language. It doesn't really get across what's actually going on, and it will get to the reason why people still talk in this way. Anyway, let's keep going. Quote, "This law is therefore not reversible. It imprints upon the universe an arrow of time, pointing the way of unidirectional change. Scientists were quick to draw the conclusion that the universe is engaged in a one-way slide towards a state of thermodynamic equilibrium. This tendency towards uniformity, wherein temperatures even out and the universe settles into a stable state, became known as the heat death. It represents a state of maximum molecular disorder, or entropy. The fact that the universe has not yet so died, that is, it is still in a state of less than maximum entropy, implies it cannot have endured for all eternity. End quote from Paul Davies. So that's some amazing stuff there, I think. An irreversible law that tells us the universe cannot have endured forever. So forget the Big Bang and expanding space-time and Hubble redshifts and so on. All you need to know that the universe actually had a beginning in time is that there is such a thing as entropy. But what is entropy exactly? Well, as he says there, it's disorder. Okay, but what's that? Is it like mass? We can measure the quantity of matter. And we can measure, well, that's called mass, the quantity of matter. And we can measure the force of gravity, or the effect of gravity on something. That's called the weight. And we can measure volumes, and we can measure lengths with rulers. But entropy, how to quantify that? So I'll come back to Paul Davies. That was the first of his books that I ever read, and I recently bought his most recent book, What's Eating the Universe and Other Cosmic Questions Here. And it too has a chapter all about time's arrow, the second law. So I'll come back to that. And don't you love the the title, What's Eating the Universe, which really is bringing the concept of online clickbait into the world of popular science publishing. But that aside, it is actually a great book. The chapters are very short, almost little blog posts. Again, another sign of our times, perhaps. But chapter 16 of the book is titled, What is the Source for Time's Puzzling Arrow? So I'll make some remarks about that chapter. And there's a third book here that I want to mention. There's many books that I'm going to be referring to, but not all of them will get a name check. But I have to name check this one. It's called A Cultural History of Physics by Carol Simoni. And it's an absolutely beautiful book. I've got the hardcover version. Very hard to find now, though, in hardback form anywhere. I've been looking for other copies of it. Very, very difficult to find. But if you can get a hold of it, if you have someone in your life who absolutely loves physics, then this is the gift for them. It's obviously a history of physics, but it's got all sorts of little gems in there, like little biographies of the physicists and nice clear images of original texts and diagrams taken from, the original work of like Newton's Principia, or Descartes' own notes, or the sections on quantum theory have quotes from dueling physicists trying to understand what the heck was going on exactly, pages from Einstein's first article on relativity and so on. And yeah, I understand. All of this stuff can be found online these days, but having it in one place, in chronological order as well as a history of physics, that's really nice. As I say, you could find it online, but here someone else has done all of the hard work for you, and the author unpacks what it all means from the perspective of the time, what they were understanding, the philosophical problems they were having at the time, and from our perspective now, given what we know but what they couldn't have. So actually, I'm going to go to that book right now and read from a section which indicates the kind of subtleties of language in this area of thermodynamics that I've mentioned already, and how there has been this resistance at times in the history of science, and in physics in particular, to take seriously the best prevailing theory at any given time. So on something like heat, as I've already spoken about, Simoni, he writes himself, the author of the text writes, one would expect that ideas concerning the nature of heat would have been based on a conception that was already widespread at the end of the 17th century, namely that heat has its origin in the motion of the particles that make up the material body. This would have led directly to the connection between the two forms of energy, heat and kinetic energy. However, that is not what happened. In a seemingly superfluous and at first glance surprising detour in the history of physics, the kinetic theory of heat was abandoned, and in its place, a theory of heat substance, caloricum, was adopted. It is only the result of our hasty judgment about what should have happened that names such as Joseph Black have fallen into obscurity. Although we owe our thanks to him for such quantitative concepts as heat quantity, specific heat, latent heat, melting point and boiling point, It has also been forgotten that findings in Carnot's and Fourier's theory of heat that are seen today as fundamental and used in teaching are based on the theory of caloricum, based on this theory of heat being a substance. And that is why there is this misconception in our language that we inherit today. I should have said end quote there, but you get the picture. And in that bit that I just read there, you might have noticed a quibble as well. Simeoni is praising Black for the concept of heat quantity, but heat quantity itself is also one of those very misconceptions someone like Atkins is trying to help us understand isn't a thing. So let's just move past that. That can be a little speed pump. And Simeoni brings up Joseph Black, a name who's fallen, as he says, into obscurity, because actually he did as much as anyone and should be credited with some of the first formulations of the laws of thermodynamics. Joseph Black was Scottish, and he lived from 1728 to 1799. He was a professor of chemistry and medical science. And Black taught James Watt, among others. And he introduced the concept of specific heat, as was mentioned just there. Now, what's specific heat exactly? Well, Feynman explained it as being like the absorbency of a cloth. Some cloths, like, tissues, can hold very little water before becoming saturated, while others, like a sponge, can hold much more water. Specific heat, or let me talk about specific heat capacity. It's the quantity of energy that a substance can hold, or more precisely, the quantity of energy taken to raise the temperature of a substance. Or, if we want to be exact with this, it is the quantity of energy, usually in joules these days, required to heat a unit mass, usually in kilograms, by 1 Kelvin, which is equivalent to 1 degree Celsius. Basically, if I have a 1 kilogram lump of metal, like a lump of iron, and I put it over a flame for 1 minute, its temperature will rise quite a lot. It has low specific heat capacity. It doesn't take much energy to raise its temperature. As compared to if I was to take 1 kilogram of water, which is a litre of water, and use the same flame to heat it, presumably it's in a saucepan of some kind or a pot, in 1 minute you don't get anywhere near the same temperature rise as what you do with the iron. There is an inherent property, therefore, an inherent property of substances that determines how much their temperature rises given some change in their internal energy. Now, what's internal energy? Well, we'll come back to that. Another concept that Joseph Black was first to figure out was latent heat. And it's a similar idea. If you have 1 kilogram of water and it's boiling at 100 degrees Celsius, then there's a certain quantity of energy it takes to boil away all of that water. In other words, to change 1 kilogram of water in its liquid form at 100 degrees Celsius into its gaseous form at 100 degrees Celsius. That's what latent heat's all about. Now, for other substances, if you've got 1 kilogram of it, let's say 1 kilogram of pure alcohol, and it's boiling, the amount of energy it takes to change its state from liquid to gas is less. That's what latent heat is. And there's latent heat for solid stuff turning into liquid stuff, and latent heat of liquid stuff turning into gaseous stuff as well. Or in some cases, solids straight into gases in the case of carbon dioxide, let's say. So this idea of specific heat and latent heat, it can be a little bit confusing, because right there, if you're Joseph Black and you have some sound concepts like that, latent heat and specific heat, easily tested and measured in the chemistry lab, it looks for all the world like latent heat and specific heats are kinds of heat, and thus heat is something that is itself a thing of a kind, a substance of a kind. So there's a quantity of it in stuff, so to speak. And when you increase the temperature of something, the heat goes up, and decrease the temperature and the heat goes down. And surely it's common sense that if you heat something strongly enough, like a metal rod that I was talking about earlier, you heat one end and eventually the other end gets hot too. Why? Well, the common sense theory goes that the heat is flowing, conducted, so we say, along the metal. Now, as I explained before, that contains misconception. It's not like it's utterly wrong. I don't like to say anything like that is utterly wrong. It contains some truth, but it also contains important misconceptions. But to explain more fully those important misconceptions with that whole view of heat, let's do a pass of the 4 laws as, well, let's say I would normally explain them if I had to teach this stuff. And this will allow us to understand the misconceptions in this idea of heat flowing from here to there. from hot bodies to cold bodies and bodies having heat in them and so on and so forth. And by going through these laws of thermodynamics, we'll be able to then, before the end of today's lengthy episode, come back and linger on the deeper implications of the second law in particular. This will set us up well, I hope, for what constructor theory has to offer that's new, and we'll be able to introduce Chiara's chapter on heat and work. So let's begin with the Zeroth law. And the Zeroth law basically forces upon us the concept of temperature. Why is it the Zeroth law and not the first law? Well, just because of history. The first law was found first, and later it was understood that prior to understanding parts of the first and second law, we needed a law governing what temperature was, what temperature did. So temperature is this interesting concept in and of itself. So they introduced the Zeroth law later on. Temperature is degree of hotness or coldness. And that's fine, you can say that, but it's qualitative. Now, you could say that temperature is the thing that a thermometer measures, and that's also true, but we want to know what it's measuring precisely. What is it that's going on causing the thermometer to indicate one temperature rather than another? Is it quantity of heat? Well, we've already said that's not a thing, but even if you imagined it is, you might imagine something like the red hot nail compared to a bath full of boiling water. Now, the red hot nail might be 1,000 degrees Celsius. The bath of boiling water is cooler by a factor of 10, but if a torturer gave you the choice of holding either the nail or plunging into the bath, there really is no choice. Choose the nail. Sure, you'll burn your hand, but you won't be dead. The bath contains far more energy, even though it's at a much lower temperature. So temperature has something to do with intensity rather than quantity. Intensity of what though? Yes, I know I've already told you, but we're going to make this more precise. If you consider the air in a room at 30 degrees Celsius, then most of that air is made up of nitrogen. Nitrogen exists as N2 molecules, two nitrogen atoms joined together. And at 30 degrees Celsius, a nitrogen molecule has an average speed of about 500 meters per second. They're zipping around all over the place. Now, if you increase the temperature of the room, the average speed of the molecules will also increase. Aha, maybe that's it. The temperature is a measure of the average speed of the particles. Well, that's all very well, except that if the nitrogen is at 30 degrees, and that corresponds to 500 meters per second, what about the chair in the same room as the air? The chair is made of wood or metal or plastic, and its particles are not zipping around at 500 meters per second. They're just vibrating in place. So this is a bit of a problem because although it is true that increasing the temperature of a body increases the speed of the motion of the particles, particles have different masses and they're bonded to each other more or less strongly. So it can't be a one-to-one thing of that a particular temperature corresponds to a particular particle speed in general. So we need a somewhat more precise conceptual understanding of temperature. We might have more luck if we weren't just talking about speed, but we were talking about kinetic energy of the particles, because kinetic energy takes into account the mass of the particles as well. But still, can we have something straightforward that everyone can agree on and then move forward? So here's one basic idea. If I've got two bodies, A and B, that are in contact and isolated from the environment, then if A is hotter than B, energy moves from A to B until A is no longer hotter than B, nor B hotter than A. They have become equal in some way. What is it exactly that has become equal between them? Well, the temperature has. More precisely, we say that A and B have the same temperature when they are in thermal equilibrium. One statement of the zeroth law of thermodynamics is, if A is in thermal equilibrium with B and B is in thermal equilibrium with C, then C and A will be in thermal equilibrium. So it's a law of thermal transitivity, effectively. The zeroth law implies the existence of a thermometer. It's the device in thermal equilibrium with its surroundings. So none of that statement of the law even implies the existence of particles, you will notice. As Atkins famously says, you can do classical thermodynamics even if you don't believe in atoms, end quote. But of course we do know about atoms now. So as a result, we have this thing called statistical thermodynamics, which is an account of what is happening according to the laws of thermodynamics in terms of particles or atoms. It's statistical because we are less concerned about what individual particles are doing and more about aggregates or averages that give rise to the bulk properties that we do observe. It was Ludwig Boltzmann, in the 1800s actually, who provided a view of temperature that is connected to particles, and I've already hinted at it. The thing about Boltzmann's view from statistical thermodynamics is that it provides some insight into quantum theory, which came a little later. If we've got a glass of water at room temperature, then we know that left long enough, the water evaporates away. How is this possible? Doesn't water only change state from liquid to gas when it boils? How can we explain evaporation that happens at any temperature? Have you ever wondered that yourself? Like, why is it that, if water changes from, if you ask what temperature does the water change from liquid into gas, people will say, well, at the boiling point, at 100 degrees Celsius, if you're not an American using Fahrenheit, let's say. But then, how does evaporation work? Why should it be the case that at any temperature less than the boiling point, at the temperature at which the liquid turns into a gas, that you still get a liquid turning into a gas? What the heck is going on? Well, water can change in its liquid form into a gaseous form at any temperature because the temperature of the water, in terms of the particles, has something to do with the distribution of energies of those particles. And those particles have a range of energies. Not any energy that you like, that's quantum theory, they must have specific energies, but they can have a range of energies. Some, at any given temperature, most of them will have a certain kind of energy or be grouped up into a particular kind of energy, but some of them will have much less energy than the average and some will have much more energy than the average. So maybe you can see where I'm going with this. In any average typical glass of water at room temperature, there will be some small number of water molecules in your glass of water that have the lowest possible energy they could have. And that corresponds to energy at or very close to what would be regarded as 0 Kelvin. So some molecules of water in a glass of water at room temperature can't vibrate any slower than not at all. And some will be vibrating basically not at all. They won't be moving hardly at all. They'll have almost zero kinetic energy. Therefore, their temperature corresponds to something like 0 Kelvin, minus 273 degrees Celsius. Not many of them, of course, but some. Most of them will have energies that correspond to the room temperature. But if you don't accept that, well, you have to accept that, well, some of the water molecules in any given room temperature glass are literally boiling away. They're evaporating. They have the energy required to change the state of the water from liquid into gas. There is some such energy needed to do that. As the temperature of the water rises, a greater and greater proportion of the molecules, of the water molecules, begin to occupy those higher energy states. Hence, more of them are turning into gas, achieving escape velocity from the rest of the liquid. That's why evaporation tends to increase as the water increases in temperature. Now, the energy of particles, like molecules of water, comes actually in three kinds. It comes in what I've already mentioned, vibrational, which is all that solid particles can do. They're just fixed in place and they're vibrating because the bonds that hold them together aren't going anywhere. But then there's also rotational. And rotational energy is the kind of energy that your particles get once they've entered the liquid phase. So the bonds break and now they're able to rotate around one another, still in contact, still weakly bonded to one another, but in physical contact with one another. They're still vibrating, but now they're actually also able to rotate. And that's in the liquid phase. They can slide around each other once those solid bonds are broken. And then finally, if you add a little more energy, you get translational energy as well. So the particles are still vibrating, they're still rotating, but now they can move from one place to another. And then we have the gaseous state. That's what happens to move from solids, where the particles are vibrating, fixed in position, to liquid, where they're vibrating, but now they're also able to rotate because the bonds have broken. And then once all the bonds are effectively broken, the intermolecular bonds that exist in liquids, like water, once they're broken as well, Although you have vibration and rotation, you now have translation. So they're the three modes of kinetic energy that you can have. Now, you can quantify this. You can quantify this using something called the Boltzmann distribution. And that puts a precise number, the parameter beta, on how the energy of the molecules at some temperature are distributed. I won't go into that. Suffice it to say, there is a simple equation, beta equals 1 over kT, where T is the temperature in Kelvin temperature, and K is the Boltzmann constant. The higher the T, the smaller the beta, and vice versa. Temperature is thus a measure of the distribution of energies of particles in some substance at equilibrium. So that's what T is, that's what temperature is. The Zeroth law has forced upon us, has explained the concept of temperature for us, either classically as that quantity which is equal when two bodies are in thermal equilibrium, or in terms of particles as that quantity which indicates the distribution of the energies of the particles in that body. So that's the Zeroth law. Well, what's the first law then? Well, the first law is energy conservation. The idea here is that however much energy there is at the beginning of the universe, that's how much you have at every other time, at any other time in fact. Pick your year or moment after the Big Bang, and you've got the same amount of energy in the universe then as what you had at the Big Bang. But there's a little more to it than that. The Zeroth law introduced temperature and refined its meaning for us. The first law is really about trying to get at what we mean by energy, especially internal energy. But let's begin with energy in general. Let's define something in physics. I said I didn't like to get fixed on definitions, but here's one that we can use that's very useful and that people don't have quibbles with. A force applied over some distance is work. Work equals force times the distance. The work has to be done in the same direction as the force. It makes common sense. You try to move your fridge, it takes some force to overcome the friction on the ground. Someone asks you to move the fridge 5 meters, that's one thing. That's a certain amount of work for you to do, a certain amount of effort. But to move it 50 meters, that's something else entirely. Lots more work, literally. So work really is motion against some force. And in fact, lifting is the best way of envisioning this. You lift a weight vertically against gravity and you've done work. We're speaking in Newtonian terms here, of course. So a capacity to do work is important. You can lift a 1 kilogram mass with your hand, but presumably so could an electric motor attached to a pulley. So the motor can do work. And maybe that motor is powered by an electric battery. So the battery has capacity to do work as well. Or maybe some coal can be burned and that drives a turbine that lifts the mass. The coal has capacity to do work. So this capacity to do work, that's energy. Or is it? We might come back to that. Maybe there are some kinds of energy that can't do work. Anyway, as a first pass, that's the idea. Capacity to do work is energy. And work is the capacity to exert some force over some distance. Energy. These concepts have something to do with the common sense notions that we have of these things, work and energy, but they're sharpened up by physics. Now there's this standard high school physics experiment. It's due to Joule, who first performed the experiment where basically a falling weight over a pulley drives some paddles that stir some water in a perfectly well insulated as you can manage, container of water. And the water's temperature, it goes up. You can measure it. Because the work done goes straight into the water, and from there, well, it's in the water, it can only cause the temperature to rise. What's any of this prove? Well, it shows that work, the falling of a weight, can be used to heat water. You can convert work into heat, and vice versa, of course, as my little Stirling engine showed. But with this experiment, this is Joule's experiment, in the high school lab, you can make some precise measurements and show that using an actual heater to heat the water requires the same energy. You can use equations like energy equals power times time, or equivalently energy equals voltage times the current times the time. And they can be used to calculate the work done by a heater of known voltage and current running for some time to heat some water. Now, who cares about any of that? Well, that introduces this idea of path independence. It does not matter how the temperature changes come about, whether by heat or by work, the effect is the same. But although earlier we were talking about kinetic energy of particles and so on, here, in this case of rising temperature, we can talk about the specific number of joules of energy imparted to the water. But we don't measure temperature using joules. So what happens to these joules of energy imparted by the heater or by the paddle? What have they gone into? Well, they've gone into the water. But again, not as a separate fluid of some kind. After all, the paddles weren't doing anything but agitating the water. We say they have gone into a quantity we call the internal energy, and we use the symbol U for the internal energy. So the internal energy of the system, of the water. When the temperature rises in a system, like a cup of water or whatever, we say that U has increased. So something has increased here. Yes, the temperature has, but also the number of joules have increased. Where? In the internal energy of the water. Now, what the internal energy is exactly, we don't need to worry ourselves about exactly if we're doing classical thermodynamics. We just know that it's gone up or gone down, because then we can calculate the change by making measurements. But if you want to know now, and I'm going to come back to this, the internal energy is the sum of all the kinetic and potential energies of the particles that make up the substance, and perhaps even also the mass energy. But calculating the total internal energy of any given substance, well, no one ever bothers with that. We're only ever interested in the change in internal energy. That's the most relevant thing for when you're building engines and so forth. Now, if we imagine Joule's experiment, where the paddles spin and the temperature rises, there's no heater there. It's just mechanical motion. The thing is, if we take away the insulation, then more energy is required in order to achieve the same rise in temperature. But why should that be? Where is the energy going? We know, it's common sense. It's going into the surroundings because the thing's not insulated anymore. But what this shows profoundly is that energy, therefore, is of two types. You do work on something that's well isolated and the temperature rises because you've increased the internal energy of the system in the water. But if you remove the insulation, then you must do more work because the energy has gone somewhere. Where? Well, there has been a transfer of energy to the environment, and not by work. Hence we need this other word. Hence we have this concept of heat. The reason the energy has been lost to the environment is because there is a temperature difference between the water now, which is warmer, and the rest of the environment around it, which is cooler. As Atkin says, this transfer of energy as a result of a temperature difference is called heat. So that's what heat is. Again, heat is the transfer of energy as the result of a temperature difference. As I quoted him earlier, it is not the name of a thing, but rather the name of a process. We can measure the energy transferred as heat, therefore, simply by determining the work done on the system when well insulated, and then measuring the difference between that case and when the insulation is removed. The difference is the energy transferred as heat, usually to the environment. Now, there is no such thing as perfect insulation, of course. So if work is done on a system and that changes its temperature, its internal energy, then the work done is never exactly equal to the change in internal energy. Why? Because some heat is lost to the environment. And that's what we're going to come back to. So energy is transferred to substances either by work or by heating. In the case of work, what is going on is that there has been, at the level of some particles, some uniform motion of the atoms. In the case of Joule's apparatus, the molecules are all pushed in the same direction by the paddles. That's what work is. Work is force over a given distance in the direction of the force. So all the particles end up moving in the same way. But when a substance is heated, that's not uniform motion of the particles. Rather, there is an increase in the random motion of the particles. Their kinetic energy, either of translation and vibrational rotation, increases. That's what heating is. So there we have the differences. Why both of these things can cause a temperature rise, but one is an average bulk motion all in the same direction, that's work, or randomly sort of causing all of the particles to speed up in their motion. Both is motion of particles, it's just that one is work and one is heat. But if mind you, if and only if, there was a perfectly insulated container of water and you did work on the container of water, then the amount of work done would be transferred to the water entirely and be represented as a temperature increase. The first law says that the work done, W, must be equal precisely to the increase in internal energy, U, of the system in that case. So W would equal delta U, Work equals the change in internal energy. And that's the first law for a perfectly isolated system. Of course, if it's not perfectly isolated, then W equals delta U plus Q, where Q is the energy transferred as a consequence of heating. So that is the first law, that the work done is equal to the change in internal energy, but plus heat, the heat lost to the environment, let's say. Now, normally texts and so on actually write that first law as delta U equals Q minus W. To emphasize, I think, we can measure only changes in U, not any absolute amount of U. U is the internal energy, so it's the sum of all the kinetic energies, the motion, and the potential, the bond energies of the particles. And as I say, presumably it can also include things like the mass energy as well, if you like. So that's the first law, which means we're at the second law. And at this point, I'm just going to hand things over wholesale to Peter Atkin and his book called 4 Laws That Drive the Universe, and the beginning of his chapter on the second law. Now here, I'm going to be reading from page 49, where Atkins writes, quote, "When I gave lectures on thermodynamics to an undergraduate chemistry audience, I often began by saying that no other scientific law has contributed more to the liberation of the human spirit than the second law of thermodynamics. I hope that you will see in the course of this chapter why I take that view, and perhaps go so far as to agree with me. The second law has a reputation for being recondite, notoriously difficult, and a litmus test of scientific literacy. Indeed, the novelist and former chemist C.P. Snow is famous for having asserted in his The Two Cultures that not knowing the second law of thermodynamics is equivalent to never having read a work by Shakespeare. I actually have serious doubts about whether Snow understood the law himself, but I concur with his sentiments. The second law is of central importance in the whole of science, and hence in our rational understanding of the universe, because it provides a foundation for understanding why any change occurs. Thus, not only is it a basis for understanding why engines run and chemical reactions occur, but it is also a foundation for understanding those most exquisite consequences of chemical reactions, the acts of literary, artistic, and musical creativity that enhance our culture." End quote from Atkins. So that's pretty amazing stuff, and it really is why people like Paul Davies and other popularisers make such a big deal about the second law. What Atkins says there puts the second law of thermodynamics into a sort of different category to others. It is elevated to this place where it is invoked alongside not only physics and chemistry and engineering, but also art. So let's get a little technical on this and go back to Atkins, who writes, quote, "As we have seen for the zeroth and first laws, the formulation and interpretation of a law of thermodynamics leads us to introduce a thermodynamic property of the system. The temperature, T, springs from the zeroth law, and the internal energy, U, from the first law. Likewise, the second law implies the existence of another thermodynamic property, the entropy, symbol S. To fix our ideas in the concrete at an early stage, it will be helpful throughout this account to bear in mind that whereas U is a measure of the quantity of energy that a system possesses, S is a measure of the quality of that energy. Low entropy means high quality, high entropy means low quality." End quote. But what does quality mean? Here's the way I used to think about this, and I can't remember where I heard it first, but I know Brian Cox used it in one of his documentaries. Presumably, we both got it from the same common source. Anyways, the metaphor goes like this with a little bit of local adaptation. Here in Australia, we've got some very nice beaches. There is one on the south coast I've been to many times. It looks like this. It's called Hymes Beach, and it's close to where my parents live. It's famous if you move in some circles because it's said to have among the whitest sand anywhere in the world. Just look at it. So if you go there on a typical Australian summer's day in early January, say, and you go without shade and without sunscreen, you will get sunburnt. The sun is intense in Australia in summer, especially in places like Hymes Beach. Sunburn is caused by ultraviolet light, UV light, comes down from the sun and it can burn you. Okay, because sunlight is bright. Now, throughout the course of a day, that sunlight, that bright sunlight from the sun comes down beaming all day long, heating the sand as well as the water. But let's concentrate on the sand. It heats it all day long for a good 10 hours or so, ignoring the less bright times of sunrise and sunset. So it's unsurprising that at night, once the sun is gone, the sand is still warm and it will gradually cool over the course of the night. But anyone who goes to the beach will know that beach sand is warm even well after sunset. What's going on? Well, the first law of thermodynamics, of course. The heating of the sand during the day by the sunlight causes a change in the internal energy of the sand, and that is noticeable by a change in temperature of the sand. The heating happens because there is a temperature difference between the sun and the sand. The sunlight has a higher temperature and it heats the sand, which is cooler, and it does all this by radiation. Very well. Bright sunlight heats sand. Okay, easy. So at night when the sun is gone and it goes dark because the earth is facing away from the sun, the same first law holds. And the temperature difference between the sand and the cool air and the dark sky now means that the same processes happen, but in reverse. The energy gained from the sun is now lost to the atmosphere, which is then lost to outer space. The sand heats the air above it and it gradually cools. Heat gained by the sun during the day is lost by the sand at night. And this goes on day after day, year after year, eon after eon, and just as well, because if it was not the case, and there was not this equilibrium, this equality between energy in and energy out, if the energy gained by the sand from heating by the sun during the day was not all lost at night by an equal amount each day, then the sand would be hotter the next day, and the day after that, and the day after that. It wouldn't be long before the sand was so hot it was glowing red hot. But that doesn't happen. There is a relatively constant temperature of the sand during the day and during the night. All the energy gained on Monday is lost Monday night, only to be regained again on Tuesday and lost Tuesday night, and so it goes with no net increase of energy by the sand. The quantity of energy gained equals the quantity of energy lost. Energy in equals energy out. All the energy is accounted for. None is lost from the universe or created from nothing. Okay, fine, common sense. That's the quantity of energy. Well then, here's the question. If the energy that comes from the sun in the daytime is in the form of UV light, which can sunburn you, and visible light, which helps you see, as well as some other things, then why at night is it not radiated back into outer space as UV light and visible light? In fact, it's only irradiated back to outer space, broadly speaking, as infrared radiation. So what's happened to the UV and visible light? Is that all being reflected? No, it's not all being reflected. The infrared radiation from the sun is not the only kind of radiation from the sun that's absorbed by the sand. The sand, like a human skin, also absorbs UV light, and that's coming from the sun during the day. We know we absorb it. We know that skin absorbs UV radiation because we can get sunburned. But if that UV radiation and the visible light is absorbed by the sand, why can't we get sunburned at night as the UV light is re-emitted back into outer space? For that matter, why doesn't the sand glow with visible light at night so as to return all the visible light energy it absorbed during the day? Well, this is the thing. Although the quantity of energy is the same, absorbed during the day and emitted at night, the type of energy is not. The energy absorbed during the day is degraded in this process. At night, the high quality stuff, the UV and the visible light, is all of it degraded to a longer wavelength, lower frequency, lower quality, less useful kind of energy at night as infrared radiation that our eyes cannot see but our skin can feel. The overall quantity of energy re-emitted at night is the same, but the quality has changed. It's been reduced. And this quality of energy can be quantified as a thing called entropy. The entropy has increased. Now, I said there in that account, the energy from the sun becomes less useful as it's re-emitted to outer space at night. What does that mean? Well, here we can turn to some history and Sadi Carnot, another great name from thermodynamics from the early 1800s. He looked at how to make engines more efficient. Long story short, I'll just give you the punchline to this bit of science. The efficiency of an engine that converts heat into work, in other words, how much of the heat will be converted into useful work, is given by this equation. The efficiency equals 1 minus the temperature of the sink divided by the temperature of the source. So here we had the Stirling engine going on earlier on, and my cup is the source of energy, and the sink is the rest of the environment here in my room. This is the formula for maximum efficiency. So today it's like 23 degrees Celsius in here, and my cup is 98 degrees Celsius there. But that's all in Celsius. We need to convert things to Kelvin to get this equation to work. So we've got the temperature of the sink, or the environment, is 273 plus 23. That converts it into 296 Kelvin. And the temperature of the source? Well, it's about 98 degrees, that water. It's not quite boiling, but 273 plus 98 gives me 371 Kelvin. Now, putting all this into our equation, 1 minus 296 over 371, that works out to be about 0.2, 20%. Isn't that pitiful? Now, the way to improve this is to have higher temperature of the source or lower temperature of the sink. Ideally, let the sink temperature approach absolute zero. Or, ideally, let the source temperature approach infinity. But how do you do either of those things? Real-life engines run on fuels that burn at particular temperatures. Real-life sinks are the environment of the Earth, which have a fixed temperature as well. The sink, the environment, is why the energy is lost as heat in these situations, and why that energy becomes less useful. We need the sink to push the heat energy away so that the bits continue to move around, because we need those temperatures to be as far apart as we can get them in order for the thing to move quickly, to be efficient. Or considered another way, let's imagine a power station. Here's a good diagram of a coal-fired power station. I say this diagram is good because it emphasizes as really important this thing here. This thing here is the cooling tower. Whenever you see pictures of power stations, you see these things and they usually have water vapor coming out. Environmentalists use those pictures to imply that's the pollution. Well, if you think water vapor is pollution, well, that's your business. They should be showing the smokestacks, which are these things. Problem is that the smokestacks almost never have any visible smoke coming out because modern power stations, coal-fired power stations, they filter out the particles. The only thing that's coming out really is carbon dioxide. But anyways, why not in a situation like this? If the power station is doing its job, converting heat to work, why waste the heat coming out here? Why not capture it here? Well, just like that. What about another turbine? Then that can generate some more electricity. Why waste that heat? Why let it escape off into the atmosphere? Sure, the hot steam can do less work as it passes through the first turbine, but who cares? Let's capture it anyway. Well, the problem is that means the steam slows down here, slowed down by the second turbine. So things begin to pile up and it begins to heat up. Everything begins to heat up. So for this turbine here, the temperature here and the temperature here quickly approach approximately the same. The efficiency reduces. The only reason this is spinning at all, this first turbine, is that the steam is high pressure here, low pressure here, because the lower temperature here. So it's rushing to fill the low temperature void. But if you put another turbine there in an attempt to capture that lost heat, to do work with it, the only thing that happens is this turbine slows down. And so whatever you think you've gained here with the second turbine, you've lost from the first. You can't actually gain anything. As some people put it with the first law, they say the first law is a statement of how you cannot win. In other words, you cannot get work done for nothing. So sometimes people say that. The first law is you can't win. The second law is you can't break even. And the third law is you will always lose. Not precise, not quantitative. So anyways, here we have it that in systems for converting heat to work, the process cannot be perfectly efficient. And some of your work is lost as heat. So you have some heat here and not all of it becomes work. By necessity, it has to be lost. And that's an irreversible change. We cannot capture that heat out there somehow and bring it back into our power station. Doing so increases the temperature and in the long run slows down the whole thing, grinding it to a halt. If it was an isolated system, the whole power station, what would happen? Thermal equilibrium, and that would mean zero motion anywhere. Now, just to drive this point home a little further, because we did, if you remember the parable of the beach, Himes Beach, where I was talking about how although ultraviolet light and visible light are coming down, amongst other things, onto the beach, onto the sand, heating the sand throughout the course of the day, in the evening, what is re-emitted back into outer space is the same quantity of energy but not the same quality of energy. The energy has been degraded to longer wavelengths of light. And so ultraviolet light is not coming from the beach during the nighttime. With the power station, something similar is going on. What's happening here is that the energy is degraded after it's done some work. So that this heat energy here is of, we say, higher quality. But the heat that's coming out here is of lower quality. It has less capacity to do work. And remember right at the beginning of all this, I was talking about how energy is that thing which has the capacity to do work. That's what we said a definition of energy could be. However, in this case, we have energy that is not quite so capable of doing work. As I said, after all, one thing that the naive person might think is that we could put another turbine right there in order to capture the heat energy coming from the first turbine and not waste it. After all, it's just being let off into the atmosphere there. But as I said, that's merely going to cause the temperature here and the temperature here to eventually equalize. And if those temperatures are equal, then this thing is going to stop spinning. There's no reason for it to keep going because there's no reason for a pressure differential anymore between this point and that point if the gas in both places is at the same temperature. And so therefore we say that the energy has been degraded. There has been an increase in entropy. The energy is able to do less work. And in the limit, the heat energy lost into outer space is actually energy unable to do work. Perhaps even in principle, it is unable to do work. And so then we say, well, what does it mean to say that all energy is this thing that has the capacity to do work when some of it does not have the capacity to do work? Well, it's an interesting scientific philosophical question that we can get into. If we originally defined energy as being that thing that could do work in principle, but some of it, after being degraded by the second law, is ultimately unable to do work, even in principle, then what is it? Well, it's still energy of a kind, but it's degraded and unable to do work, and therefore violates what we originally said energy was. This formula of Carnot's for efficiency, it's worth reading what Atkins actually says about it in his book, one of his books. And Atkins wrote, quote, "Carnot's analysis established a very deep property of heat engines, but its conclusion was so alien to the engineering prejudices of the time that it had little impact. Such is often the fate of rational thought within society, sent as it may be to purgatory for a spell." End quote. That's worth keeping in mind when we think of David and Chiara's work on all this. Anyways, this problem of the power station can be summed up in what is known as the Kelvin statement of the second law of thermodynamics, which is no cyclic process is possible in which heat is taken from a hot source and converted completely into work. Notice that. Something is said not to be possible, which is a counterfactual claim. The science of can and can't. So I'll read it again. No cyclic or cyclic process is possible in which heat is taken from a hot source and converted completely into work. Now, I really have to go back to Atkins here and just read what he says about this and about cold sinks. Quote, "There must be a cold sink, even though we might find it hard to identify and it is not always an engineered part of the design. The cooling towers of a generating station are, in this sense, far more important to its operation than the complex turbines or the expensive nuclear reactor that seems to drive them." End quote. Yes, so the heat sink is a crucially important part of these thermodynamic systems so that you can have this transfer of energy from the hot to the cold, which is the thing that does the work. There's another way of putting the second law, and it's kind of inconvenient that there are this variety of ways of putting things, qualitatively speaking, but quantitatively it turns out they can be shown to be equivalent. The other way of putting the second law is known as the Clausius statement of the second law, which goes like this. The change in entropy equals the heat supplied, reversibly, divided by the temperature. Basically, entropy is disorder. A gas has got high entropy. A solid, being all ordered and crystal-like, has low entropy. All the particles are there lined up like soldiers standing at attention. A change in entropy is a ratio of energy in joules of heat transferred to the temperature in Kelvin. So the units of entropy are joules per Kelvin. And so yet another way of putting the second law is that the entropy of the universe increases in the course of any spontaneous change. And this is what, Paul Davies makes a big deal about, and what, many physicists make a big deal about. You've got this irrevocable increase in the entropy of the universe. In other words, the system and the surroundings is what we mean by the universe. So whatever change is going on and the rest of the universe. So that's the universe. So this leads to some misconceptions. The system or the surroundings can have a decrease, a local decrease in entropy. For example, biology is a highly ordered thing, right? Biological systems are highly ordered. And so this leads to these misconceptions where people try to, I don't think they do it so much anymore, but creationists, intelligent designers used to say things like, well, we've got this law of thermodynamics that says that entropy must always increase. But biology is a thing that violates that. After all, biology is a decrease in entropy, therefore miracle. Well, no, of course not. Okay, you can have a local decrease in entropy. That's what a fridge does, by the way. It cools things and you have a decrease in entropy inside the fridge. But it is expelling entropy, an increase of entropy to the rest of the universe. Same too with biology. The sun is shining on the earth and heating the earth and causing all sorts of increases in entropy everywhere else, even if locally with the knowledge being created inside of organisms, you have a decrease in entropy there in the organism. But the organism is causing an increase of entropy in the rest of the universe. We can go right down that rabbit hole with entropy. It's all very interesting and subtle and so forth, but this is already a super long episode. So I might leave the technical discussion of disorder, exactly, but it's probably worth going over. It is worth going over at least a more precise definition of entropy, or understanding of entropy, as I like to say, rather than definition, in terms of what's happening with the particles. So let's consider particles at a fixed temperature. And remember what a particular temperature means. It means that the particles have a distribution of energies, and that distribution is called the Boltzmann distribution of the energy of the particles over the allowed energy levels at a given temperature. Now, here's the thing about energy levels. For a given volume of space, they're different to other volumes of space. There are fewer permitted states or energies that some collection of particles can have in a smaller volume. You can imagine a microscopic box like this one. And in that microscopic box, only certain energies are allowed according to the laws of quantum physics. That's just the way it is. Don't get upset. The universe is discrete in that way. You can't just have any energy that you like. You can have this energy or that energy or that energy, but not just any energy in between these. So let's say we have this tiny, tiny box. Let's say this is to scale. And these are my particles in this box at some temperature. And let's say that's 100 Kelvin. Tiny little box there. And there's your particles, and they're the energies that they have. This is the ground state, so to speak, the minimum energy, all the way up to this is the particle with the highest energy. And there are what? 1, 2, 3, 4, 5, 6 energy levels here permitted inside of that box at that particular temperature. Now, the thing is, that volume of space accommodates those certain energy levels. They are the energy levels permitted by particles in that volume. But what if we increase the volume of the box by widening it, keeping the temperature the same? Well, this is what happens to the energy levels. You see, they then become closer together. So now, instead of only having 6 energy levels, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can have more. And so the particles distribute themselves across more energy levels. The energy levels get closer together, more are permitted in this box. Okay, that's because the box is larger. So the Boltzmann distribution spans more energy levels at the same temperature. So we have a different entropy. More disordered simply by virtue of the fact there are more energy levels permitted in a larger region of space. Or another way of putting this is to say if we were to randomly select a particle from the first box with the aim of getting it from the first level, the chance of getting a random particle from that first level in the second box is lower in comparison because there are fewer there. As Atkins puts it, quote, the disorder and the entropy increase as gas occupies a greater volume at the same temperature, end quote. which is right for people too. Consider everyone squashed into a classroom. That's all quite ordered. Now you let them out into the playground. Disordered. Just for completion of the technical stuff. The formula normally taught for entropy is this one, which is the entropy S is equal to K log W. Here K is the Boltzmann constant, just as before, and it appears in our definition of temperature as well. S is the entropy, but here W is not the work, but it's the weight of arrangement of particles, the ways the particles can be arranged to achieve some amount of energy. But anyways, that's the formula for total entropy. Now, all of that is second law. And we're going to talk about that again in the next episode and a little bit more before the end of this episode. But we really have to go on and just mention, without going into too much detail, the third law of thermodynamics. And the third law of thermodynamics, and it states that the entropy of a system approaches a constant value as the temperature of the system approaches absolute zero. So different substances, different systems will have different minimum entropies, but that greatest amount of order will be achieved at absolute zero. So you'll end up having a constant value at the minimum possible temperature. But I'm not going to get hooked on the third law of thermodynamics. So before I finish up today, and well done for persevering, I have to go, as I promised, to Paul Davies' latest book and the chapter all about time's puzzling arrow. Davies writes in his latest book, quote, I'm not reading the entire chapter, just a part of it, quote, boiled down to its essentials, the issue with time's arrow is this. Imagine taking a movie of an everyday incident and playing it in reverse to an audience. Everybody laughs because it looks so preposterous. People walking backwards, rivers flowing uphill, sandcastles washed into shape by retreating waves. But in physics, a laugh test isn't enough. What exactly gives the game away? Here's a clue. Open a new pack of cards. The manufacturers arrange them in numerical order by suit. Shuffle the cards. The sequence will now be jumbled. If a magician shuffled a pack of jumbled cards and gave them to you in numerical order, you'd know you were being duped. While it's not impossible for jumbled cards to be randomly shuffled into order, it's exceedingly improbable. The arrow of time here is clear. Random disruption turns order into disorder. Scientists zeroed in on this basic property in the middle of the 19th century. The Austrian physicist Ludwig Boltzmann considered how gas molecules rush around randomly, banging into each other and spreading heat energy around. He analysed this natural shuffling mathematically and identified something called entropy, a precisely defined quantity that measures the degree of disorder in the gas. Then he used Newton's laws of mechanics plus an averaging assumption to prove that entropy would never go down. The rise and rise of entropy is one expression of the so-called second law of thermodynamics, perhaps the most inclusive law in all of physics, because what's true of gases is true of everything. All systems have a natural tendency to grow messier, to degenerate and decay. Just skipping a little. And I'm picking it up where he writes, understanding the cosmic implications of all this, the British physicist Lord Kelvin delivered a lecture in 1852 famous for what has to be the most depressing prediction in the history of science. The entire universe, claimed Kelvin, is dying, slowly choking on its own entropy. Gradually, inexorably, cosmos is turning into chaos. And then Davies goes on to say, if the relentless march of disorder defines the arrow of time, then the universe must have been more ordered in the past. And indeed it was. As I have been at pains to point out, the universe that emerged from the Big Bang was astonishingly, bafflingly, extremely highly ordered. Had it been exactly ordered, the arrow of time would have stalled because perfection persists. It would have been a case of blandness forever. Gravity would have nothing to get its teeth into. But of course, the nascent universe wasn't 100% perfect. There were those ever slight wispy spludges found by COBE, a mere 0.01% variation in temperature, far below what the human senses would register. Pausing there as my reflection. COBE is the Cosmic Microwave Background Explorer. It is this satellite, here it is, it looks like this, first credited with detecting these so-called anisotropies in the cosmic microwave background. These anisotropies are fluctuations in the temperature. Previously, we thought that the cosmic microwave background, the heat left over from the Big Bang, was extremely uniform, 2.7 Kelvin. That's just above absolute zero, but uniform in all directions, so exactly 2.7 Kelvin everywhere that you looked, unless you take extremely precise measurements, with a microwave detecting satellite far above the atmosphere of the Earth. And so the first images that came back looked kind of like this. Now, this is an anisotropy. It's a dipole, in fact. Here it's slightly warmer, here it's slightly cooler. Now, the reason for this, it's an artifact of the fact that we are moving through the galaxy. In fact, the galaxy is moving through space, and so that can be subtracted from the image, and you end up with something like this. And that red band through the middle there, well, that should look familiar. That's the Milky Way, and that can be subtracted out of the image as well using image processing. And finally, you end up with the image that everyone was after, which is this, the first image of the cosmic microwave background, showing the slightly warmer and slightly cooler regions. The slightly cooler regions are the slightly more dense regions, which eventually go on to condense into the matter out of which everything that we see in the universe is made. So all the galaxies end up condensing out of these slightly more dense regions, and those warmer regions are the voids in between where clusters of galaxies and so on and so forth are. It was the first satellite that detected evidence of the cosmic microwave background radiation, the heat left over after the Big Bang. The person given the Nobel Prize for Physics for finding this was George Smoot. His student was his graduate student, who I think was the first one to really analyse the data and then hand the data to Smoot, was Charlie Lineweaver, that famous physicist I often talk about, who also has worked with Paul Davies, taught me as well. He was one of my lecturers. So yes, I heard a lot about Kobe and those stories about Kobe during lectures. Anyway, continuing. Splodges he's talking about. Splodges in the images taken by Kobe, and Davies goes on to write, quote, "The splodges betray a minute departure from orderly perfection, a palette of almost imperceptible density perturbations in the primordial plasma. Gravity set to work on the splodges, the overdense regions pulled more strongly, drawing in on the surrounding material and amplifying the density contrast, generating large-scale complexity. Clusters of galaxies, churning clouds of gas and meandering stars. Clumping is gravity's gift to the cosmos." And I'm skipping a part here, and I'll pick it up where Davies concludes with, "Thus it is that gravity, the incubator and annihilator of habitable order, is also the source of time's pervasive arrow. The time asymmetry that distinguishes yesterday from tomorrow, memories from anticipation, birth from death, can be traced back to the birth of the universe itself, and specifically to its extraordinary degree of primordial smoothness. But where did that smoothness come from in the first place? Do we just accept it as an unexplained initial condition, a big fix? One possible explanation is that an appeal to the tiny violation of time reversal symmetry in certain hard-to-discern particle processes. Did the very particles of the universe themselves come with their own inbuilt arrow, which somehow projected itself onto the entire cosmos in the torrid aftermath of the Big Bang? Maybe, but in my view, not very likely. Far and away the most popular explanation for the smooth start to the universe is the inflationary scenario. A burst of anti-gravity propelled expansion in the first split second creates precisely that almost, though not quite perfect, uniformity. But that's still not the end of the trail, because the universe has to get itself into an inflationary state at the outset. How did that come about? The scientific community is still very far from reaching a consensus on these thorny issues. All that can be said for certain is that one of the most fundamental properties of the physical world, that tomorrow is different from today, still lacks a full explanation. And it lies high on my own list of essential, unanswered, big questions. So that's Davies. Now, the question is, if so many other approaches to trying to understand the origins of this second law have hitherto not borne fruit, neither from quantum theory, nor general relativity, nor string theory, maybe constructor theory has something to add here, and it does. That's where we will leave it today, so that next time I can get straight into readings from the book itself. Actual readings from the Science of Can and Can't. So even though this is misleadingly titled, it's something to do with the Science of Can and Can't, we didn't actually get to any readings. So until next time, bye-bye. Oh, and one thing, I'll make a personal appeal. If you'd like to support this enterprise, for want of another word to describe it, see my Patreon or PayPal. The links are there on my website here at www.bretthall.org. Bye-bye.